Hello. So this is the second lecture of the Simple ICTP course on anti-self-door equations and integrable systems. So first, let me remind you what we have done yesterday. So this course is about a relation between anti-self-door equations in four dimensions, namely the anti-self-door Yang-Mills equation and anti-self-door conformal equation. Both of these equations are integrable by themselves, integrable by twistor method. And it turns out that many non-integrable systems in lower dimension can be realized as symmetry reductions of these two equations. Okay. So in this lecture, I would like to focus on this side of this diagram. So I will be talking about anti-self-door Yang-Mills equation. And so the outline is here that, so I divided it into three main parts. So the first one is I will try to define what anti-self-door Yang-Mills equation is. And then we will look at some examples of reduction of the equation and one of the integrability feature, which is the lax pairs. And then finally, I'd like to discuss geometric interpretation of the lax pair, which would lead to the twistor method for the integrability of anti-self-door Yang-Mills equation. So yesterday we started on this one. So let me. Okay. So anti-self-door Yang-Mills equation, it is in fact, it is a system of equation, a system of PDEs, of matrix PDE, where these matrices are actually components of the connection one form. And so the equation is to impose a condition on a connection of vector bundles. And as I mentioned yesterday, that I would like this course to be very introductory. So I will start from defining a vector bundle and connections. But to do that, we would need some definitions and basic concepts about manifolds and tensor fields, which I started to recall yesterday. Now, so I will continue with this. Okay, I'm sorry to go to the top. I forgot to. Right. So yesterday we have defined manifolds, and we were looking at tangent vector fields, but not yet. So we start on tangent space. Yes, so we have defined that. Suppose M is a smooth manifold, and this symbol denotes the set of smooth functions on M. Then a tangent space to M at a point, it is a space of linear maps, which maps a smooth function to a real number that it satisfies the product rule here. Yes, and each linear map, we call it tangent vectors at P. Yes, and so yesterday, I think we ended up to here, I think, that an example of a tangent vector at a point, the one that is very popular and very useful, we will use it later, is coordinate vectors. So with this symbol for the coordinate vectors at P. And so we defined it that when it acts on a function to give a real number, it's the same as a partial derivative of the coordinate representation of that function evaluated at the coordinate, the point, the representation of the point P on Rn. Okay, and it can be shown that this set of coordinate vectors is a basis for the tangent space. Okay. Right, so let's continue. So that this was yesterday. So let's continue from here. And I because I realized that I've gone very slowly yesterday. So today for recalling about definitions of manifolds, I have written almost everything so that to go quickly, and I will start right again when we look at vector 1 to define vector bundle. Okay. So next, this is tangent vector at a point, and I would like to define tangent vector field. Okay, so I want to talk about tangent, not just the vectors at a point, but tangent vector field. So this is the same as vector field that you are familiar with from vector calculus. The picture is like, suppose it's manifold, and the picture is like, it's like a field of vector. You attach a vector to each point. So in fact, tangent vector field is a rule that you assign a tangent vector to each point. And the way to define it, one way to define it properly is to start from tangent bundle. So the tangent bundle is disjoint union of each tangent space at each point in the on the manifold. Yes. And so it can be shown that this is also a smooth manifold as well, but of 2n dimension. So this is like a diagram, a rough diagram for the tangent bundle, is that you have a manifold. I write a manifold as a line, a manifold M here. And at each point on M, you attach, you have the tangent space at P, like this. So the whole space is a tangent bundle. And there is a natural projection map from the pi, from the tangent bundle to M, just by this projection. Yeah. Now, from the tangent bundle, we can now define a smooth tangent vector field so that it is, let me just say, so that it is a map that for each point P, it is assigned a tangent vector at that point. So it assigns an element of the tangent space. So if you change point, you have another, you assign another one. So so the picture would be like, this is a tangent vector field. So at each point, it's a rule that assigns each element of the tangent space over that point. And so it is defined by this map here. So it is a smooth map from the manifold to the tangent bundle. And the only requirement is that when it composite with the projection map, it will be the identity. So when we go up by y and we go down again by pi, it's the same point. It just says that when at each point, when you assign the tangent vector, it has to be the tangent vector at that point. Okay. Right. So this is a vector field. An example of a vector field that is also useful is the coordinate vector fields. So it's just the vector field that at each point is assigned the coordinate vector at that point. Then because as we have before we have that this tangent vector, the coordinate tangent vector is a basis. right? So this is a basis of the tangent space. Then, and because of this, from this, you can show that for any vector field y, you can write it as in this form. So this form I'm using the Einstein summation convention. So I'm summing over A over the repeated index. Yes, so and y is a smooth function. Just because if you evaluate this at each point, then this will be tangent vector, and you just write it in this basis here. So let me just go back up here. Strictly speaking, so suppose you have a vector field y, it values at a point, say yp. So I use this to denote its value at a point p. Then it is a point on the tangent bundle, which strictly is a pair of p and then some tangent vector above p. But then for convenience, often we would just write yp equal like this. Just forget the first argument. And this is what I'm written here, but for convenience, maybe we just write like this. Okay. Now, since yesterday we have seen that a tangent vector, in fact, we define a tangent vector to be a linear map that maps a smooth function to a real number and satisfy the product rule. Then from this action of the tangent vector, we can define how a tangent vector field acts on smooth function, that it maps a smooth function to a smooth function. And this action can be defined in this way, that we say that the vector field acts on smooth function and give you a function, right? So this is a function, and this function evaluated at a point p is a real number. And then this is the same as you take the value of the vector field at p, which is the tangent vector, and acting on this function. Okay, so by this definition, point-wise, you can define an action of vector field on a function, and then you have to prove a bit that this will be smooth. And actually, you can prove that a smooth vector field can be identified with a linear map, like this, that map a smooth function to a smooth function and satisfy the product rule. Okay, now let me next go to, we have tangent vector fields. Now there's tangent covector fields. Before we go to fields, let we consider cotangent vector first. So we define the cotangent space. In fact, I think it's wrong. Cotangent space at a point P and M is manifold. We define it to be just the dual space. So I will use this symbol for the cotangent space of P. Before this, we have TPM, which is symbol for tangent space. And then now I will just put star here as a symbol for cotangent space. And we define it to be the dual space of the tangent space. And where the dual space is just a space of real valued linear map on the tangent space. that is an element of the cotangent space of P, it is just a linear map that map tangent vector to a real number. An example of, and we call this, sorry, we call an element of the cotangent space the tangent covector, and sometimes I would just say covector. And an example of a covector is a coordinate covectors, yes, which is defined by a unit symbol for a coordinate covector P. Then we define it that when it acts on a coordinate vector, it would give you a real number by definition, right? But we define it so that when it acts on a coordinate vector, it satisfies this equation. Yeah. So it will be 1 if the index are the same, and it will be 0 otherwise. And these coordinate covectors are very useful because they form a basis for the cotangent space. Okay, and we would say that this is a dual basis to this one. Okay, so next, so this is covectors, tangent covector at a point P. Then we want to define covector fields over a manifold. Again, we use cotangent bundle, which is a disjoint union of the cotangent space at each point. Can we have the same thing as before, as when we defined vector field, that you have the cotangent bundle and a covector field. A covector field is a way that it's a rule that you assign to each point on the manifold tangent covector. So it's like this black line I draw here. And yes, a formal definition is that it is a map, a smooth map from M to the cotangent bundle, such that when you composite with the projection map pi, then you get the identity. An example of a covector field is a coordinate covector field. So this is the one that assigned to each P a coordinate covector point. And again, since the coordinate covectors form a basis for the cotangent space, you can, from this, you can show that any covector field can be written locally in a coordinate neighborhood in this form, where this is a smooth function called component functions. And that a useful identification is that a smooth covector field can be identified with a map that map a smooth tangent that map the vector field to a function. Yes, and the way we define this action is that a covector field acts on a vector field, give a function, and this function is defined by saying that its value at a point, which is a real number, is the same as the covector, which is the value of this covector field at a point P acting on the tangent vector. Yeah, and from this definition, because when covector acting on vector, it is linear over R, then it will follow that this covector field, when it acts on vector field, it is linear over smooth function, the set of smooth function. Right. So we have vector fields, co-vector fields. Now we extend to tensor fields. And there are different types of tensors, but in this lecture, I will concentrate on covariant tensor. Okay, so first, let me record the definition of a covariant tensor at not on manifold yet even. So a covariant tensor on a vector space. Yes. So suppose we have a vector space V, capital V, then a covariant tensor of rank K, where K is a natural number. Sometimes I would just say K tensor. It is a multilinear map that it maps K vector of V to a real number. Okay. And it is multilinear means it's linear in each argument. And I will use the symbol TKV to denote the set, which is in fact a vector space of the covariant K tensors on V. And you see, if K is 1, then it is just a linear map on V, a real valued linear map on V, which is just a covector. Next. There is a useful product to divide between tensors. So if so S is a K tensors and T is an L tensor, then the tensor product, I would write it like this, is tensor with T. We defined it to be a map that acts on K plus L vector and give you a real number. And the way it acts is that if you give K plus L vectors to the tensor product of S and T, then you just feed these vectors to S and T in order, like this. So S will act on x1 to xk and T xk plus 1 to k plus L. Like this. And because S and T are multilinear, the tensor product will follow that the tensor product is multilinear as well. So it is a covariant tensor too of rank K plus L. And a very useful result is that suppose you have a basis. So this is a basis of the dual space of V. Then the tensor product, so it's a covector, right? So this is a covector, and you tensor K of them. So this is covariant K tensor. Yes. And it can be shown that this, when the index A1 to AK can be any number from 1 to n, this form, this is a basis for the space of covariant K tensors. Then for any K tensor, you can write it like this using the Einstein summation convention. So this is a real number, the components of the tensor, and which in fact you can get this real number component by let T acting on this E, and there's a misprint. This is BK. Where this capital E, this set of vectors is a basis that is dual to E here, to little e here. Okay, so this is K tensors on a vector space V. Now we go on to a manifold. For manifold, we have a vector space, a natural vector space at each point on a manifold, which is the tangent space. Then we can consider covariant K tensors on the tangent space, and everything just follows. So the dual of the tangent space is a cotangent space, and which has in the cotangent space, for the cotangent space, P, it has the coordinate covectors, the set of coordinate covectors as a basis. Then we can use this. So I'm using this result here. Yes, I'm using this result here, applying to the tangent space of on a manifold. So we have that this set is a basis for the space of K tensors. Right, and so this is the K tensors at a point, and if we want to define a tensor field, we can do the same as before, that we start from defining the bundle of covariant K tensors as a disjoint union of the space at each point. And we just define the covariant K tensor field to be this map that assign to each point on the manifold a covariant K tensor above at that point. And this locally, any K tensor field can be written in this form, where well, here we have extended the tensor product to tensor fields, which you can do it pointwise. So what I mean is, suppose you have two tensor fields, say sigma and tau. So you can define the tensor product pointwise. That it will be another tensor field that its values at the point is the tensor product of the values of each tensor field, like this. And so this is the tensor product I use here, right? And any K tensor field can be written in this form, where this is the coordinate covector field. Okay, now we come to the last topics that I'd like to recall about manifolds and tensor fields before we go to vector bundles. That is differential forms. So what are differential forms? So they're just K tensor fields that we have just seen, but they have a certain property that, so they are smooth K tensor fields, but with the property that they are totally antisymmetric. And this word we can also use instead of this word, the skew symmetric or alternating. So they're the same. Right, so let me start by reminding you what I mean by totally antisymmetric. and start with a tensor, a covariant tensor just on the vector space, not going to the manifold yet. Yeah, so we say that a K tensor is totally antisymmetric if its values if its value when it acts on K vectors changes sign whenever you interchange a pair of arguments. And I will use this symbol, capital lambda K V, to denote the set of totally antisymmetric K tensors. Now, for a general K tensors, we have defined the tensor product. I think say S and T, we have defined the tensor product of a covariant K tensor. But suppose S and T are totally antisymmetric, this tensor product will not be antisymmetric as well. So we have another product just to preserve this property, and this is called wedge product. That suppose we have a totally antisymmetric K tensor and omega, and then our tensor eta, then we define the wedge product, or another word, exterior product, to be a K plus L covariant tensor that obtained by this. So you just do the normal tensor product, and then you antisymmetrize it. So that to make it become a totally antisymmetric tensor, and this symbol, let me just go down. This symbol ALT just means antisymmetrization of a tensor. Yes, and so antisymmetrization of the tensor product of omega and eta, which so for any K tensor, we define antisymmetrization by that when it acts on a K vectors, then it's given by this. So it is a sum. So we consider permutation of the arguments and sum over all permutation and weighted by a sign. So it's permutation of 1 to K, like this. And if it's even permutation, the sign is +1. If it's odd permutation, the sign is -1. And then you just have to weight it by K fact. This is because this weight is due to that we want the definition to be so that if the tensor is already totally antisymmetric, then the antisymmetrization will give itself. So of T will be T itself. Okay, so this is the wedge product. And you could try you can try to use this definition and verify, and the example I'm written here, that if omega and eta is just it's just a co-vector of, so a tensor of rank 1, then the wedge product will be given like this, and it follows from the definition. Now, another useful thing about wedge product is that before we have that the tensor product of K covectors. So now I'm going on a manifold now. So a tensor products of K covectors is a basis of it's a basis of the space of K tensors on this tangent space. Then, but if we look at the space of totally antisymmetric K tensors, which is a subspace of this. So this is a subspace. This. Then it can be shown that this set is a basis for the subspace. It is the wedge product of K covectors. And I would like to note one thing. You see that the basis, the set of bases, the index are different from here. So here the index can be any number from 1 to n. So it can be repeated. But here we have that it must not be the same. And the reason is due to a property of the wedge product of one form, and you can see from let's here from this example, you see that it's between the wedge product between, I'm sorry, not one form, a covector. The wedge product between the covector is anti-commute. Yes, so you have this. So this means that if you have the same index, say dx1 wedge dx1, it will go to 0. So we don't want the index to be the same. And also that we use this this ordering. We have to use the ordering too, because from this property here, you have that dx1 which dx2 will be minus dx2 which dx1. So that there is a relation between this, so they're anti-commuting. So that's why we use this ordering, so to get rid of this relation. Hence, any totally antisymmetric K tensor can be written in this form. Here, I don't use the isolation convention because of this condition on the index. But then if we want to use the isolation convention, we can also do it. But then we have to divide by K fact. This is to get rid of the redundant from the relation like this. Right, so this is our totally antisymmetric K tensors at a point, but now we can look at a field of it, and a field of totally antisymmetric covariant K tensors, we call it differential form. And we can define this via bundle as before. Yes, so we start from the bundle. Oops, sorry. We start from the bundle, which is the disjoint union of each of the spaces at each point, and then we just define the field of these tensors, like we did before. Yeah, so it's a map like this, and so this is differential K form. Right, and so we nearly finished this recalling before we go to vector bundle. Just two more things. So the first one is we can extend the wedge product from the tensor to tensor fields, so to differential form. And suppose I use this omega km to denote the set of differential k forms on M. Then we define the wedge product between k form and an L form pointwise like this. Yeah, that its values at p is the same as the wedge product of the value of each one, and this is a k plus L form. And this property of wedge product we will use later, that the bilinear, so linear in each argument, and associative and anti-commutative. If we swap the argument, you have this sign is -1 and to the power k multiplied by L. Before this, we just have the property for one form, the covector extend to one form, that you have just minus sign here because it's 1 times 1. And let me just give you like for references the coordinate expression for the wedge product, because we will have to use this in computation later. That so first, for k form, you can write it like this. So in terms of the wedge product of the one form or the covector field, coordinate covector fields, this, and these are functions, component functions. And then the wedge product of K and L form, which we defined it above here. We defined it pointwise, like this. It can be worked out that it will be in this form. So the component of the wedge product, yeah, you just it will be like this, that it will be just anti-symmetrization of the components of omega and eta, and with some weight. Yeah. And this anti-symmetrization of indices. So we define it similar to the anti-symmetrizations of tensors that we just looked at before, that we just sum over all permutations and then weight it with a sign. For example, if you have covariant two tensor alpha and with index A and B, then anti-symmetrize, this will be case 2, and then you just the two index, so you have A, B, and then B, A, and with some weight. Yeah. Okay, now last thing, this is before we finish with this, is I need to say about exterior derivative. So this is how we can differentiate a differential form, say, right? So let's start with first a zero form. So in fact, a one form is a covector field, and we define a zero form to be just smooth function. So just if you write if you, but I rarely use the symbol, but if you use this for zero forms on M, then this is the same as smooth function. Okay, now, so there is a differentiation of a function that, so the differential of function. So we define it like this. So on a manifold, suppose f is a smooth function, then we define the differential of function to be a covector field or one form, denoted by df, like this. And we defined it to be by this equation. So a one form is you can identify it with a map that maps a vector field and give you a function. Then you define the differential. You define this one form to be the one form that when it acts on x and give you a function, it's the same function as when this vector field x acts on this function f for any smooth tangent vector fields on them. And from this, you can write a local expression for the differential form like this in terms of the coordinate covector field. And here, I would just say what this is. So this is a symbol for this vector field. So it is just the coordinate vector field curl by QXA and act on F. But I would just write it like this. And by definition, you have to go, if you haven't seen it before, you have to go back to definition we looked at. This is a function, and it is this function, its value at a point P is the same as the partial derivative of the coordinate representation of it at the coordinate representation of P. Now, so after we define differential, then we could look at if we look at a smooth function as a zero form, we can think of a differential as an operator that sends a zero form to one form. Right? And then you could think of look for an operator that map any k form to k plus one form. And there is a theorem here which says that on any smooth manifold and case any natural number, there is a unique linear map that does this. So it sends a k form to a k plus one form such that it is an extension of the differential. So when we look at a zero form or smooth function, this operator D is a differential. And so it's a differential of it. Okay, and it satisfies a product rule as we would want from a differential operator that if D and of the wedge product of omega and eta, then it follow the product rule, but it's a graded product rule that if the D passes through a K form, then you have -1 to the power of K. Yeah. And the third property, which is it is a property of the differential, and we would want it for this map as well, that the square, which is D composite with D, is zero operator. And okay, I would just give a local I'll end this with a local expression, and this is the end now. Because we might have to use it later, that locally in any coordinate chart, D of a form of a K form omega, which is if you write a K form omega in in a coordinate basis like this, then this unit operated in the theorem can be given by local formula that it just is equal to the differential of the component function and with the rest. Yeah. And we have a local expression for differential of function that is, so this is just dx. Is it just this? And from here, it follows that the components of exterior derivative of a K form is given by this. You just have to write it down. Right, so with this, I finished recalling all the definitions of a manifold, and I would like to now go to talk about vector bundles and connections and curvatures in order to define anti-self-Dou-Yang-Mills equation. So I think this is an hour now, so let's have a break for a bit. So, okay. So let's have 5 minutes break and I will start again at 3. Okay, so now I'd like to, well, in this chapter, I want to define anti-self-Dou-Yang-Mills equation, which is a condition on connections on a vector bundle. So I will start from defining vector bundle and connection on vector bundles and curvature. Then after this, I will be able to say what anti-self-Dou-Yang-Mills equation is. Okay, and in this part, I follow the references. So the book, I is still using Book of Lee on manifold, on smooth manifold. And then I followed the book by Ward and Well, and also Mason and Woodhouse. Okay, so the full title of the references, I gave it in the reference page here. So we will look at, follow this, and another one. Yeah. Right. Okay, first start with vector bundle. So in fact, we have seen vector bundles. Those are the tangent bundle is an example of vector bundles, and cotangent bundle, this is what we had before, and the bundle of covariant K-tensor. So all of these are examples of vector bundles. So from this, in fact, from these examples, you can see roughly the structure of a vector bundle. So you have kind of a base, a manifold, like a base. And then at each point on your base, you have a vector space attached to it, right? If it's a tangent bundle, then you have the tangent space attached. But in general, if it's any vector bundle, you have you have a vector space attached to this called a fiber at each point. So at each point you have a vector space, and the whole thing, the total space, you call it a vector bundle. Right, so let me write down the proper definition. So M is a smooth manifold. I abbreviate it like this. Then smooth real. For the moment, I will talk about real vector bundle first. Real vector bundle of rank n, capital N, over the manifold M. So it is another smooth manifold, like the total space here. E, but with a map, a projection map, pi from E to M, like a projection from the whole space onto the base, like we had before for the tangent bundle. We required it such that the projection map is onto and smooth. Let me draw some picture. So suppose this is the base manifold, and you have a total space, E, which is another manifold. And you have a map pi, which is onto and smooth. Okay. Then second property, that for each point Pn, the preimage under pi of a point P is a vector space. So this is like the tangent space that we have for the tangent bundle. So the preimage under pi, this is, and I will denote it by E and subscript P, is a real vector space. And we call this fiber over P. And if we say we are defining a real vector bundle of rank n, then this is a vector space of dimension capital N. Okay. Later, I will be talking about complex vector bundle as well, but I will define it later when we use it. In that case, then the fiber will be complex vector space. We will see it later. Okay, the last property. What we want is we want it so that locally, say like if we have some open set in M and then we look at the pre-images under pi and we have some locally. The last thing I'm going to write here is that locally, this local region look like a product manifold. So suppose this is U, so this local region look like U cross I. And we have to define precisely what I mean by look like. So 3 is that again for each point P and M. So there exists a neighborhood U containing P and a diffeomorphism phi, and I just put a subscript U to just to say that this is associated to U. So this map the pre-image of U to the product manifold here. And we want it so that let me just write it. Maybe let me just write it here. Oops, sorry. Maybe I'm sorry, maybe I write it first and then I draw some diagram later. So diffeomorphism to this product such that for each point Q in this neighborhood, when we restrict this diffeomorphism onto just the fiber, this will be a map from the fiber over Q to this, to just Q cross Rn. And this map, and it is an isomorphism because this is a vector space, it's isomorphic to Rn. So this is an isomorphism, so R linear isomorphism. Okay, so let me draw some diagram. So what I mean is we have a base manifold M and a total space, the tangent bundle E and a map pi and P is a point in M. At each P you have a neighborhood U. and the map phi u map this neighborhood to the product u cross Rn. Okay, and such that we want this phi to be such that it maps a fiber for any point q in u, so it map the fiber pq. In fact, it can map to in general, it could map to any subset, right? But then we want it to be mapped over to this, to Q cross Rn. And also we want it to be isomorphism. So from this to this is an isomorphism. So this is like we have a local representation of the vector bundle as a product manifold. Okay, and this map phi is important. It is called local trivialization. So we end the definition here. Let me give you a summary first. So a real vector bundle is a structure. Maybe I just talk from this picture. It's a structure. It's a smooth, M is a smooth manifold, E is a smooth manifold, and there is a map pi which is on to M and smooth. And then over each point in M, the pre-image and the pi is a real vector space of, if dimension n, then this bundle is of rank n. Then we wanted that locally it looked like a product space like this, where it mapped each fiber to the corresponding, like over Q to Q cross Rn, and it is an isomorphism. And this map phi is called local trivialization. A simple example is the product manifold itself. Say E is M cross Rn. Then this is clearly a vector bundle, and which admit a global global trivialization. Phi, so I don't put a subscript U because it's over the whole M. So phi is just the identity. And we have a name for any vector bundle that admit global trivialization. It might not be a product manifold, but we would call it trivial bundle. So say that a vector bundle admitting a global trivialization is called a trivial bundle. Okay. Now, so this is a simplest case that you have a global trivialization, then the bundle, we say the bundle trivial. But this means if the bundle is non-trivial, then you have you don't have a global trivialization. That means you have several local trivialization like this, right? Like in this picture. Yeah, so you have phi subscript u, so it's a local trivialization over u. Then to cover the whole manifold, the whole base manifold, you yeah, you might have another, well, you might have another, so this is V and you have another local trivialization over V. Then, but we would want things to be consistent over the overlapping region, like when we define the manifold. Okay, so let's look at this. So there's a lemma which says the relation between the two local trivializations when the overlap region is non-empty. Suppose we have a smooth vector bundle. And suppose we have two local trivialization. Phi, which is trivialization over U. This, and another one psi, say over another open neighborhood of MV. So let these be local trivialization. Where, and we assume that the intersection is non-empty. Okay. Then in the, oh, let me just write down a bit before writing properly. So in the overlapping region, I think I have to draw pictures. So maybe let me finish the lemma and I'll draw a picture to explain. Okay, this lemma says then what are the relation between these two local trivialization? Then there exists a smooth map of G. It is a map that from the domain is this overlapping region, and it maps a point in here to a matrix, an invertible n by n matrix. So it mapped to the general linear group, such that this composition, and I will have to draw to see what this is. This composition which is a map. Is given by okay, so let me just draw a diagram to explain what I just wrote down. So we have a vector bundle over M, and two trivialization. This is V, and this is U. So this is the primate of V under pi. The trivialization, well, psi, map this to V cross ion. And then on this side, okay, and on this side, this is pi U, and the local trivialization phi maps this to U cross ion. Right. Then you have the overlapping region. Now, this map here, phi inverse composite with phi, is this one. Yeah, psi inverse composite with phi is this one. So if we look at each point P, so P, sorry. So if P is a point here, and you have a fiber, EP, yeah, then this fiber is mapped to, over here, it mapped to, this is P cross RN. And over here, it's also P cross RN. Now, if we look at an element, so if you have an element on the fiber, here, it will be P, say V, suppose V an element of Rn, but if it mapped by this local trivialization, it will be P and this, let's say V tilde, another, it doesn't have to be the same, another element of Rn, right? Then, because when because when the local trivialization, when we restrict, by definition, when we restrict it onto a fiber, it is an isomorphism on a vector space between vector spaces. Then this composition is an isomorphism as well. And since it is an isomorphism, invertible, the relation between V tilde and V will be given by invertible matrix. So this is why you have, I'm sorry. This is why you have this equation here, where this G, the bracket P, just to label that it depends on P. So this is an invertible matrix. Hence, if we let P vary, this will be a function. And it's a function with invertible, with values in GR and R. So it is the same G here. Okay. So this is what the this lemma means by this. Okay. Let me just note it one, just note one sentence before we go. So then this composition. Yes, which if I restrict it to this line, this fiber. So it is an isomorphism because it's a composition of isomorphism. It is an isomorphism. So we would have that. It would map PV to this, in fact, P and V tilde, but V tilde, because in an isomorphism, it has to be multiplication of V by invertible matrix. So this is an element of GL in R. Okay. And if we let P vary, you have a function, but you need to still need to prove that it is a smooth function, like the lemma claim. Like here, this claim that it is a smooth function. Okay, right. And this G is quite important. We'll see it a lot later. It's called this function G. The G is called a transition function. It like the same name of the transition function between coordinate charts on a manifold. Transition function. Another word, sometimes it is called patching matrix. Okay. Okay, let me, because I'm running out of time. I go very slowly. Let me just state one proposition which will be useful about the transition function. That for a trivial bundle, a vector bundle E is trivial. That means it admits global trivialization, right? It's trivial if and only if the transition function or transition functions. Normally there will be many because in this lemma, sorry, let me just in this lemma, we talk about one transition function because we were looking at just two local trivializations, but in general, you will have many. So you have many transition functions. And the proposition says that if a bundle is trivial if and only if all the transition functions can be factorized. Like this. And I use the index alpha beta to label different local trivializations. And the transition function would be defined on the overlapping region. Yes, so this transition function is a map from it's a map from the overlapping region to GR in R. Now, it can H alpha and H beta is the matrix that define on each neighborhood. Like H alpha, it's defined on U alpha. It's also an invertible with value in the invertible matrix. Okay. Right, so I leave it with this, and I will mention this proposition later when we have to use it. Okay, next, there are a bit more things about vector bundles that I need to introduce before we define connection. Okay, so the next one is local section. We have seen local section before as well. An example of local sections are the coordinate vector field. So in fact, let me start with the definition, and then maybe I will talk about coordinate vector field later. I'm sorry. Let me just start with the definition. It's quick. So again, M is smooth manifold, E over M smooth vector bundle. And U is an open subset of M. Then a smooth local section of E over U is a smooth map from U to the bundle, such that when composite with the projection map pi is the identity. We have seen this many times when we talk about vector field, covector field, tensor fields. So they are examples of sections on a vector bundle. And we have the same diagram, the same picture that I drew before. But let me just say a specific example, like a coordinate vector field. This is a local section of the tangent bundle. The tangent bundle over M. And recall that the coordinate vector field is defined on a coordinate neighborhood. Suppose you have a coordinate neighborhood U with coordinate XA. I'm using indexes. So it is map from U and then to the tangent bundle. This is like what's here, such that it maps a point P to the coordinate vector. And then if you vary P, you have like this the vector field. So this so it look like a cross kind of cross section. That's why we say a section here. Okay. Well, let me add it here that if the section is defined for the whole M, not only just some proper subset, then we say that S is a global section. Let me write down some notation. That I will use later. So that I will use this capital gamma E, to denote the space of smooth section of E. And then, well, for example, a section of the tangent bundle is a tangent vector field. So this is the symbol that I used before, so it's the same. And this is the symbol I used for the differential K forms. And differential K form is a section of this bundle, of the bundle of totally antisymmetric covariant K tensors. Okay. Sometimes if I talk about local section, I might add, I might write like this, to mean local section over U. This local section, set of local section on U. Now, there are important sets of local sections for vector bundles. What I mean is, for example, the coordinate vector fields this is a special sections of the tangent bundle because if you recall, the set of coordinate vector at each point is a basis, right? It is a basis of the tangent space. Then the set of coordinate vector field are the set of vector fields such that its values at a point. Then let's just say this. So this set is an example of a set of vector fields such that their values, the value of vector fields at a point, form a basis of a fiber above each point, right? And such the set of and this is our local sections in our language now. So such a local sections are called frame fields. Let me just write here. So local frame field. And local trivialization. So a local frame field for a vector bundle E over M, its local set is not defined for the whole manifold. So over an open set U in M. So it is an ordered set of local sections say E1 to En. N is the rank of the bundle. And I would often just say EI. So an ordered set of local sections over U such that at each point in U, the values of each section at P is a basis. The set is a basis of the fiber above P. As an example is what I just talked before, that the coordinate vector field, sorry, I abbreviate, the coordinate vector field, and I'm sorry, let me change the index to I just to match here, is a local frame field for the tangent bundle. Then it is like when we write down, before when we look at vector fields, tangent vector fields, it is like when we write down any vector field in terms of coordinate vector field. Given a local frame field on a vector bundle, we can write any local section in terms of this frame field as well. So given a local frame field, over U, then any local section S over U can be written as like this. So it's similar to what we have for the tangent vector field before. Right? So something like this, it's the same. But SI is a function, is a real valued function on U, called component function. Okay. Now, an important fact, which I'm afraid I will not have time to go into details now because I'm running much slower than I thought. But let me just state it then. An important fact is that a choice of local frame field is the same as a choice of local trivialization. So we will look at them as being the same. So this is important. A local trivialization is the same as a choice of a local frame field. And then in computation later, especially when we go to anti-self-dual-Yang-Mills equation, and we have to calculate things locally, then we will always make a choice of local frame field. And if we make a choice, let me just write it. So with a choice of a local frame field, we can represent a local section just by the component functions, and you can think of it as a column vector, like S1 to Sn. So locally, you can think of local section as a column vectors whose entries are functions. Yeah, so that is all a function. And later I might abuse some notation that I might use the symbol S just to mean these column vectors instead of the local section itself, but just to mean it's representative. Okay. So I'm sorry, let me just see the time. Okay, I have about 5 minutes. So let me talk about end today with change of frame fields. change of local frame fields. It could be that you have a local frame fields, two local frame fields that the domain overlap. Then we could look at in the overlapping region, what are the relation of the representative of the section. Yeah, so suppose you have two frame fields, say E and E tilde. Two frame fields. So define over, say, U and U tilde respectively. Then suppose on the overlapping region, which is not an empty set, each the two frame fields are related like this, that E tilde J is EI with this, where G at each point, G is an invertible matrix, n by n matrix, so G is a function from the overlapping region to GR and R. So suppose the two frame fields are related like this. It can be worked out that for if S is a local section over the intersection, and suppose S is written in the frame field E like this, and with respect to the frame field E tilde like this. Then from here, you can use the above relation to deduce that the component SI is related to the S tilde by this G, by this relation here. Now, and if I want to point out that what we write here, that this component SI in with respect to this frame field related to this is the same as what we had. It's the same as what we had here for the transition function. So that G I wrote there is actually the transition function of the two local trivializations associated with the frame fields. Right? So because this is a component of the same element, but in another trivializations with V tilde. Yes, so let me just conclude it here. So the G, which is a matrix of, which is this matrix, is the transition function between the associated local trivializations with these two frame fields. So locally, you can look at it as if you represent a local section by a column vector, then it's just, you just get this column vector by multiplying with matrices, the column vector with matrices. This. Okay. And I think I run out of time now, so I will have to stop here. So we are still on the vector bundles, and so tomorrow I hope to continue, and then so we can define the anti-pseudo-Young-Mills equation. Yes, and then we would go from there. So I think I would okay, so I end the lecture for today here. So thank you.